Differential length in the spherical coordinate system. Consider a point in this system with coordinates capital R, theta, and phi. To obtain the differential length, we change each of the coordinates by a differential amount, producing a new point in the neighborhood of point P1, for example, point P2. The distance from P2 to P1 gives the differential length along that particular variable and direction. Let's start with capital R. Suppose a differential d capital R is added to the capital R component of point P1, giving point P2. As shown in the figure, point P2 is obtained this way. The distance from P2 to P1 is simply d capital R. Therefore, dl sub capital R equals d capital R times a hat sub capital R. Now, suppose we have point P1 and we add a differential d theta to its theta coordinate to obtain P2, assuming capital R and phi remain constant. In that case, point P2 is located as shown in the figure. The distance from P1 to P2 here is in fact an arc. Theta is an angle, so the arc length equals the radius times the angle traversed. Therefore, dl sub theta equals capital R times d theta times a hat sub theta. Now, for dl sub phi, we change phi by an amount d phi by holding capital R and theta constant. In this case, little r, the distance from the axis, also remains constant. If we vary phi by d phi, then since capital R, theta, and little r remain fixed, point P2 is obtained as shown. The distance from P1 to P2 here is dl sub phi, which equals little r times d sub phi times a hat sub phi, as we showed earlier in the cylindrical system. To express this in terms of the spherical system's own variables, we note that little r equals capital R times sine of theta. Therefore, dl sub phi equals capital R sine theta d phi times a hat sub phi. We have thus shown that the differential length in the spherical coordinate system is given by this relation. Now, consider a shape like this, a very thin wire wound in this manner. Since it's a very thin wire, it can be treated essentially as a line. As shown, this thin wire is wound along the surface of a sphere, an imaginary sphere. Now, let's place this sphere in the coordinate system so that its center coincides with the origin and then remove the sphere itself, leaving only the wire. Here the z-axis, the distance of points on this particular path to the center, that is capital R, is constant, while theta varies among the points on this path. Their theta values are not fixed. These points also revolve around z, so phi varies as well. Therefore, the differential length of this particular path equals dl equals capital R times d theta times a hat sub theta plus capital R sine theta d phi a hat sub phi. Now consider this shape. This too is a very thin wire but wound in the manner you see here, as though wound around a cone. So the points on this particular path are in fact points that make a fixed angle with the z-axis. Shown here, here is the z-axis. The points on this path have varying capital R. Notice though that since they can be thought of as lying on a conical shell, their angle with the z-axis is fixed. So, along this particular path, theta is constant and the differential change in theta is 0. Phi, however, is variable since the points revolve around the z-axis and take on different phi values. Therefore, the differential length of this particular path equals dl equals d capital R times a hat sub capital R plus capital R sine theta d phi a hat sub phi. Now let's move on to the standard differential surfaces. The first surface we consider is the constant capital R surface. We define it standard surfaces as those in which one variable of the system is held constant while the other two vary, with the two corresponding differential lengths multiplied together to construct the surface, the third variable remaining fixed. Suppose we want to consider constant capital R. Take a point whose distance to the origin, that is its radius capital R, equals a fixed value capital R sub 0. Now we introduce a change in theta at this point. What results? A semicircle if theta range from 0 to pi. Now rotating the semicircle a full turn about phi, a spherical shell is produced. So the spherical shell is a constant capital R surface. Here the theta range from 0 to pi and phi range from 0 to 2 times pi, producing a complete spherical shell. The differential of this surface is the change in theta multiplied by the change in phi in the direction perpendicular to this surface, that is either positive or negative a hat sub capital R. So the S can be obtained from this relation. Let's consider another constant capital R surface. Take the same point on the z-axis whose distance capital R sub 0 This time let's vary theta from 0 to half pi, producing a quarter circle. Now rotating this quarter circle about the z-axis by 2 times pi. We see that a hemispherical shell is produced, specifically what's called the upper hemispherical shell. And as is clear from the figure, here theta ranged from 0 to half pi or 90 degrees, while phi ranged from 0 to 2 times pi. This gives the upper hemisphere its ds is the same as before. Let's also consider another constant capital R surface. This time let's take the point in the xy plane for simplicity on the y-axis. Now we introduce a change in theta at this point to produce a quarter circle. We rotate this quarter circle by 2 times pi. You can see that a hemispherical shell is produced, specifically the lower hemisphere. Here our theta ranges between 90 degrees and 180 degrees or half pi to pi, while pi ranges over its full range from 0 to 2 times pi, producing the lower hemisphere. Its ds is still the same constant capital R surface element. Now consider this same kind of surface. Take a point whose distance to the center is a fixed constant capital R sub 0. Let's vary theta from 0 to pi, but this time vary phi from 0 to pi instead of 0 to 2 times pi. In that case, we obtain what's conventionally called the right or eastern hemispherical shell. Here, our theta ranged from 0 to pi, but phi ranged from 0 to pi rather than 0 to 2 times pi. So, in effect, it's as if we sliced a complete spherical shell along the xz plane and kept the right-hand hemispherical shell. Its ds is still the same constant capital R surface element. Now, let's consider yet another constant capital R surface. The same point at distance capital R sub 0 from the z-axis. Again, we can vary theta from 0 to pi. Now let's take phi from pi to 2 times pi. In this case, we obtain what is called the western hemispherical shell. Here, theta ranged from 0 to pi, while phi ranged from pi to 2 times pi. Its differential surface element remains the same constant capital R surface element. So we observe that by adjusting the ranges, we can obtain various sections of a full spherical shell, all of which are constant capital R surfaces. Simply by varying the ranges of theta and phi, we can select these eastern, western, northern, southern hemispherical shells, or even a quarter of a hemispherical shell, that is 1/4 of a full spherical shell. All of these are considered subsets of the constant capital R category. The next standard surface is the constant theta surface. Points on this surface have varying capital R and varying phi, but a fixed theta. Consider a point at the origin and introduce a change in capital R. A line results with capital R ranging, for example, from 0 to a fixed value such as capital R sub 0. But theta remains fixed for all points on this line. As you can see, their angle with the z-axis is constant. Now, we want to introduce a change in phi along this line so as to create a surface keeping theta fixed. We rotate this line along the z-axis and a conical shell is produced in this way. So the conical shell around the z-axis is a constant theta surface. Capital R varies and phi is also varying. Here, phi ranges from 0 to 2 times pi, giving a complete conical shell. The differential surface element here is the change in capital R times the change in phi along the direction of a hat sub theta. Therefore, this becomes ds equals plus or minus capital R sine theta d capital R d phi a hat sub theta. Let's again discuss a constant theta surface. This time, we do not take the point at the origin. Suppose the point has a capital R that is not initially 0. That is capital R range, say between A and B as shown here. Now let's introduce a change in phi about the z-axis, producing a hollow conical shell of this form. This surface is likewise a constant theta surface. Looking at this from above, you can see that in this case phi ranged from 0 to 2 times pi. Suppose we make a cut in it. If we kept the right hand half phi, here ranged from 0 to pi, and we got a half cone surface. Now we chose the left hand half instead. Phi ranges from pi to 2 times pi. You can see the resulting half cone conical shell. We could also introduce two cuts into it. If we keep the lower quarter, phi ranges from 0 to half pi. All of these surfaces were constant theta surfaces. The final standard surface in this system is the constant phi surface. Suppose we take a point at the origin. Now, along a fixed theta direction, we introduce a change in capital R, producing a line. Here R varies from 0 to capital R sub 0. Now, let's introduce a change in theta at a fixed phi, producing a shape resembling a half disk. Points on this half disk surface all make a fixed angle with the x-axis. Phi is fixed, say, for example, around 45 degrees. Of course, we could also take phi in other regions, for example, around 180 35 degrees, producing this half disk. Looking at this from above, you can see that the points on this half disk all share a fixed angle relative to the x-axis, here roughly 135 degrees. Or we could take the angle between 180 and 270 degrees, such as 225 degrees, giving this kind of half disk shape. Again, the angle of these points with the x-axis is fixed. So this door-like semicircular shape can in effect be swung hinged at the z-axis. It can rotate and be fixed at any position, producing our constant phi standard surfaces. Return to our phi equal 45 degrees case. You can identify the surface better here, and it's clear that theta here has varied fully from 0 to pi, producing this half disk. Now we could also choose not to take the full range of theta. For example, if we take theta from 0 to half pi and make a cut, keeping the upper half, then for this half disk, theta ranges from 0 to half pi, and the surface is still a constant phi surface. Or if we chose the lower half of this cut, the surface is constant phi with theta between half pi and pi. Or we could choose not to start capital R from 0. In that case, we get a half disk hinged at the z-axis but hollow. Here, for example, capital R varies from, say, A to B, and theta between 0 and pi. All of these surfaces are constant phi surfaces, and their differential surface element, ds, in this case, equals the change in capital R multiplied by the change in theta in the direction of a hat sub phi. Therefore, substituting the dl's, this becomes ds equals plus or minus d capital R times capital R times d theta times a hat sub phi, which can be simplified plus or minus capital R d capital R d theta a hat sub phi. Now, the standard differential volume. For volume, we must multiply all three differential lengths together. This also requires introducing a change in capital R. Specifically, we introduce a change in capital R at a point to produce a line, say capital R ranging from 0 to A. Now we introduce a change in theta along this line, keeping phi fixed, so as to produce this half disk, say theta, ranging from 0 to pi. Now we introduce a change in phi in this half disk from 0 to 2 times phi. If we do this, as shown, a spherical volume is produced. So the sphere is in fact generated by varying all three differential length elements. We can likewise consider sections of this sphere. For example, we can produce a cone by letting capital R vary, say, from 0 to A, like this. And instead of letting theta vary fully to pi, letting it vary only up to some angle, such as theta remains from 0 to a value like theta sub 0, producing a slice of disk. Now we rotate this slice about phi. We obtain a conical section carved out of the sphere in the spherical coordinate system. The differential of these volumes equals the product of the three differential length elements. And since the differential volume is in fact a scalar quantity, substituting and simplifying gives dV equals dl sub capital R, dl sub theta, dl sub phi, which equals to square root capital R sine theta d capital R d theta d phi. We can determine the ranges of theta, phi, and capital R and substitute them in, and by integrating dV we can compute the volume of the sphere or the volume of the cone or any volume of this coordinate system.